The universe is a giant jigsaw puzzle made up of infinite pieces. We can only see a small part of it and can only guess at the rest. The cosmic abyss hides many mysteries and riddles, and there are still many ahead for us to unravel. Let's go on a fantastic virtual journey through the universe's vastness and probe its fundamentals. To begin with, we will delve into the depths of primordial chaos to understand how the cosmic order around us is formed from it and try to explain it using the anthropic principle. And then we'll try to answer this question: why are we still not receiving signals from civilizations on other worlds? Are we alone in the universe, or is there some other intelligent life somewhere? The power of imagination will reveal fantastic spacecraft that can cross interstellar space. They will help us get as far as the outermost borders of the universe and then venture beyond to see what lies further out. This journey will end in the distant future and show us what our universe's death will be like. Let's get ready. And we begin. One flap of a butterfly's wing in Brazil would be enough to cause a hurricane in Indonesia. Edward Norton Lawrence, 1893, Kyoto, Japan. Young lawyer Henry Stimson and his wife Mabel White are on their honeymoon in Kyoto. The vibrant Oriental city and its ancient history astound the newlyweds. They will remember this visit for the rest of their lives. May the 11th, 1945, Los Alamos, USA. A special U.S. Army committee lists priority targets for atomic bombings. Kyoto is at the top of the list as the largest industrial center in Japan, pointing to the city's considerable cultural significance. The Minister of Defense, Henry Stimson, crosses it off the list. This made Hiroshima the main target for the U.S. Army. Next in line and at risk of bombing is the town of Kokura. August 9, 1945, Japan. The crew of the U.S. Air Force B-29 bomber is given a specially important order by the commanders. The military arsenal in Kokura must be razed to the ground. A state-of-the-art bomb, more powerful than before, is loaded on board the aircraft for the mission. However, the town is enveloped in such thick fog that the crew cannot distinguish the target. The aircraft captain, Charles Sweeney, decides to fly on to the town of Nagasaki. Thus, some sentimental reminiscences from 50 years ago and an ordinary weather event affected the destinies of millions of people. And this story is just one of many examples where seemingly small events may give rise to major consequences, incredible in their scale. This phenomenon is commonly perceived as the butterfly effect, but it is just a part of a big field of science known as chaos theory. To better understand the correlation between small arthropods and destructive weather events, let's travel back to the recent past. In 1961, mathematician and meteorologist Edward Lorenz attempted to forecast the behavior of atmospheric flows using computer modeling. The scientist assumed he could predict the weather with unprecedented accuracy thanks to new computing capabilities. However, the results of the calculations could have been clearer to the scientist. To speed up the calculation process, Lorenz divided it into stages, so that the final results of the previous stage would be the starting conditions for the one coming next. Some of the resulting figures were slightly rounded up by the computer. This was so negligible that it was not supposed to significantly impact the final answer or the scientist's thought. However, in reality, it turned out that the results of uninterrupted and stage-by-stage calculations differed dramatically. Later, studies revealed that the system of equations Lorenz was trying to solve needed to be revised for atmospheric process modeling. Still, as is often the case, a misformulated task proved to be a step towards an amazing and unexpected discovery. In his search for answers, the mathematician found that all possible solutions to the system grouped around two conventional positions, which he dubbed attractors. If every solution were to be represented by a 3D coordinate system, it would eventually form a shape reminiscent of a butterfly's wings. Interestingly, the slightest change in any initial parameter may sharply transfer the final calculation result from one wing to the other. In fact, Lorentz was not the first to discover an effect like that. Similar ideas were expressed by German philosopher Johann Fichte and French mathematician Henri Poincaré in their works. Be that as it may, Lorentz transformed the annoying error of mathematical modeling into a potent and elaborate theory capable of answering many questions. It goes without saying that hundreds of scientists would have contributed to the notion of chaos in the decades that followed. And the theory itself has come a long way. Its mechanisms can be applied to describe such complex phenomena and processes as turbulent flows, the evolution of biological species, social interactions, and stock exchange quotes. The laws of chaos define celestial objects' movement and stars' explosions, the birth of empires and the demise of continents. To get to the bottom of these factors and regularities, first and foremost, the notion of chaos has to be defined from the point of view of science. First of all, it should be noted that any chaotic structure is subject to rather rigid and clear physical laws. But they are so complex that a system's behavior appears unpredictable. For a reason, structures like that are also known as deterministic chaos. Concerning their behavior being predefined, this principal feature distinguishes them from stochastic systems based on truly random events. If a chaotic system's behavior is supervised several times with identical initial conditions, it will react like a structure based on pure chance. Meanwhile, the result will always be different. For example, experiments show that the decay of unstable nuclei in a sample of radioactive material occurs exclusively by chance. We can calculate the approximate number of atoms transforming within a specific period, but at the current stage of technological development, it is impossible to predict the precise time a given nucleus is supposed to decay. The exact mathematical definition of chaos sounds like this. A system has to exhibit nonlinear characteristics, be globally stable, and simultaneously have at least one oscillating equilibrium point. At the same time, the system's fractal dimension must not be less than 1.5. Getting one's head around this convoluted phrase is challenging if one is a professional mathematician rather than a layman. In simple words, it may be expressed by three principal points. Firstly, the system has to be nonlinear. Let's imagine we're influencing a structure in one way or another and getting predictable feedback. It is logical to assume that after several interactions of this kind, the resulting change will equal the sum of all single ones. However, this isn't the case for a nonlinear system, and the structure will change more or less than we estimated. This was the effect encountered by Lorentz in his calculations, which prompted him to continue his studies. Secondly, a dynamic chaos system must be responsive to the initial conditions. That is, to exhibit this very butterfly effect. This means that no matter how tiny and almost negligible the change in the initial conditions may be, it may force the system to develop completely differently. Thirdly, as a system develops, its separate parts are supposed to overlap and interact. Such interactions usually need to be considered in classical physics. However, quite often, it proves to be a grave omission. Keeping track of multifaceted influence makes chaos theory models elaborate like real structures. For example, 13.8 billion years ago, just a few quanta of time would have elapsed since the hypothetical Big Bang. There is neither matter nor energy around us as we know them, and the four fundamental interactions are interconnected by one mysterious force. The physical laws known to us are not yet applicable at this point. However, others are working instead, which is just as rigid and predetermines the system's future development. At the same time, The tiniest change at any point in the germinating universe can change its future completely. Whatever the reason for this tiny change, our reality was literally born. Thanks to chaos in the scientific sense of the word, let's imagine what it's like about 1 million years later. The space then would have become more like what we know it to be, although there aren't any stars or planets. There are only countless clouds of primary hydrogen floating around the young universe. The hydrogen is exposed to gravity's pressure. This forms gravity centers which are soon to become the first stars. These gas clusters are splashed about quite irregularly, with no system. They're also massive enough to mutually exert gravitational influence. At the same time, with any protostars moved aside or with their mass slightly altered, these changes will influence their own evolution and that of their immediate neighbors. This means that the laws of chaos continue to rule the universe. In the billions of years that followed, primary stars burned out and exploded, saturating the universe with heavy elements. New stars were born from hydrogen clusters with clouds of cosmic dust near them, swirling in gigantic vortices and forming protoplanetary disks. It is easy to see their structure's already familiar chaotic movement patterns and interactions, and this is how, 4.5 billion years ago, the solar system was born. The yellow dwarf, known as the Sun, gives us light and warmth. Every single second is located on the periphery of the Milky Way as it orbits around the center of our galaxy. It follows the so-called corrotation circle. This means that the rate of our Sun's movement accurately follows the rotation of the galaxy's spiral arms, which are stellar nurseries. Thanks to this fascinating synchronization, the solar system hardly ever crosses the arms, thus keeping a safe distance from harmful supernova flares and the heat of active stars. The diameter of this galactic orbit matters too. If the Sun were to lie closer to the center of the Milky Way, the great abundance of heavy elements would have rendered the forming planets too large and massive. Besides, the galactic core's powerful ionizing radiation would have thwarted any attempts by life to evolve and propagate on the surfaces of the planets and their satellites. On the other hand, the further from the galactic center, the poorer the chemical diversity of elements. In this case, rocky planets of a rich chemical composition like our Earth would never have been able to form. At best, the Sun would have been orbited solely by gas or icy giants. There are some exciting coincidences easily noticeable within the solar system too. For example, consider this. The Earth lies at the ideal distance from the Sun and follows a stable orbit with a small eccentricity. Our planet's orbital trajectory is remarkably close to a perfect circle. If the trajectory is shifted by as little as 5% in any direction, the planet will become icebound or shrouded in a dense cloud of water vapor. The bottom line is that any advanced life forms would cease to exist. In addition, the Sun itself has several extremely important features. It is neither hot nor cold, and its life expectancy is considerably long. Even though their forms are in a wide habitable zone around a hot star, their life expectancy is generally small. Also, its ionizing radiation is much too powerful. On the other hand, the coldest stars, like red dwarfs, can sustain a habitable zone that is too narrow and generally too close to themselves. That is why, often than not, planets within this zone are tidally locked to their star and are not equally heated up, with the temperatures on the two sides drastically different. Someone may offer a counter-argument here to this effect. It wasn't the Earth that adapted to host humans, but life adapted to the existing conditions. This is a rather sensible point, although if we delve deeper into the universe's structure, some facts cannot be accounted for by this statement. First, celestial bodies can have stable orbits only in three-dimensional space. Other than that, the orbits of electrons in a substance's atoms become unstable. In other words, electrons and atoms either collapse to the core or fly away into space. Thus, atoms cannot exist in a multidimensional space. A universe of this sort would only have radiation and freely floating elementary particles. Another point to consider is that there are several fundamental values on which all contemporary physics is based. They usually include the speed of light, the gravitational constant, Planck's constant, the elementary charge, and the electron and proton masses. All these values have been arrived at experimentally and are considered mutually independent today. However, modern science cannot say why these values are exactly like that. For example, a free electron is heavier than a proton-electron system. Without this inequality, there would be no hydrogen around us. Otherwise, its atom would immediately turn into a neutron. By the same token, no stars could form without hydrogen, and heavier elements would never exist. With the values of the Coulomb interaction and the strong interaction slightly different from those gauged today, no thermonuclear synthesis reactions in stars' interiors would be possible with a high gravitational constant. Stars would compress far too strongly. This would inevitably produce many large and hot stars with a short lifespan. After they burned out, most matter in the universe would be buried inside black holes and neutron stars, never to become material to help form planets, satellites, and other space objects. By contrast, with a decreased gravitational constant, interstellar gas would not be compressed enough to make thermonuclear reactions self-sufficient. In this case, stars would never flare up, and the universe would be filled with giant brown dwarfs this time. A change in the electromagnetic interaction coefficient in any direction would render chemical reactions and complex compounds virtually non-existent. On the other hand, if the Coulomb interaction were stronger than it is now, there would be no elements heavier than boron around. Their nuclei would be torn apart by protons. Electromagnetic repulsion. Heavy elements can form in the universe thanks to several factors favorably combined. Here are some more exciting coincidences. Consider this. Thanks to a certain state of carbon, helium can transform into something known as carbon resonance. This phenomenon plays a crucial role in forming heavy elements and their spreading across the universe. Thanks to carbon resonance, stars go supernova and shed their outer layers. Atoms born in their interiors are scattered across space to form planets, satellites, asteroids, and other celestial bodies. Besides, carbon is vital for the genesis of life. Only carbon can create long, elaborate chains, forming the base for and forking into incredibly diverse chemical compounds. Life as we know it can exist only when based on organic compounds that would never have formed but for carbon. So now it is clear that the universe itself, as well as life in it and intelligent observers, that is, humans, came to be only thanks to several fascinating and not readily obvious coincidences. Theories that would be able to account for this are usually beyond the scope of physics and have more to do with philosophy. One of these is referred to as the anthropic principle. Even though the term itself was coined only in 1973, the ideas it is based on were voiced much sooner. For example, we come across this idea in the works of Soviet scientist Grigory Idlis, dating back to 1958, where it is expressed to this effect. We observe a part of the universe that is not random, a priori, but one that was made suitable for the genesis and evolution of life by its special structure. This vision is referred to as the weak anthropic principle. Much later, the so-called strong anthropic principle was formulated, according to which the universe is supposed to have certain properties favorable for the evolution of intelligent life. Or, to put it differently, an observer is needed for the universe to exist. The latter formulation is based on an idea used in quantum physics. The observer plays a crucial role because their presence dramatically influences the behavior of particles. That is why the observer is indispensable in any quantum physics experiment. We might also see it put this way. The laws of the universe are the way they are because we can only exist in the universe the way it is. The anthropic principle implies that other universes may exist theoretically, or parts of this single universe may have different physical laws. However, either humanity cannot observe those areas, or those hypothetical worlds cannot get real without an observer. This assumption may be further developed into multiverse theory or a hypothesis where basic physical constants may change their values over time. Still, observations of the areas of the universe visible to us show that the fundamental values remain unchanged. The concept of a multiverse defies description within the scope of science. Generally speaking, the anthropic principle lies largely beyond the scope of the scientific view of the world and requires a metaphysical approach. Stanislaw Lem commented on this to this effect. It's an attempt to account for the unknown by using the unknown. Also, the anthropic principle clashes with the mediocrity principle. The latter states that the area of space observable to humans isn't anything extraordinary, and there would be many similar stretches within the universe. The Milky Way, for example, doesn't boast any particularly unique structural features, and its position in the universe's large-scale structure only stands out among billions and billions of other galaxies. In addition, the principle of space homogeneity is accepted in contemporary physics, which means that natural laws are the same from point to point in space. Numerous observations of the world around us support the correctness of this postulate. Humanity has been stirred by these questions since time immemorial. Are we alone in the universe? Is our home planet unique, or are there more Earth-like worlds in the Milky Way? Or is what we see just a kind of backdrop, with whatever is behind them being something incredible that would defy our understanding and therefore appear carefully concealed from us by the universe? Science cannot yet give satisfying answers to any of these questions. Otherwise, it would bring about a downright revolution in our perception of the world and upgrade our cognition to a whole new level. As it is, everyone is entitled to their own opinion. According to the theory we'll be looking at today, any intelligent race will face several insurmountable obstacles at a certain stage of its development. And the upshot of any civilization's development is that it will meet its demise sooner or later with no traces or evidence of its existence left behind. The hypothesis we will be talking about is called the Great Filter. To estimate the plausibility of such prospects, we will have to direct our gaze into the future and speculate about issues likely to lie in wait ahead of us that we're going to encounter while evolving as a species. The idea of the Great Filter hypothesis was first proposed by the economist Robin Hanson in 1996. The theory was supposed to account for the Fermi paradox, something I told you about in one of our earlier videos. According to the author, since there are no traces of extraterrestrial civilizations to be seen in the observable part of the universe, it is doubtful that the chances of the birth of intelligent life forms are high. And so, arguments in favor of this notion have to be seriously questioned. Factors unknown to science may impede the evolution of life forms, not allowing them to grow into a civilization advanced enough to venture into the cosmos and become a galactic race. If the hypothesis were to be believed, similar factors might also get in the way of our species. As for the notion of the Great Filter itself, it specifies what some of these obstacles may be like chronologically. They can be either in the past, when animals are prevented from evolving to become intelligent species, or in the future, meaning that there is a big hazard of an intelligent civilization almost certainly finding itself on the road to self-destruction. In our case, the concept implies that the easier evolution has occurred until now, the worse the prospects for humankind appear to be for the future. In other words, if we still need to deal with our Great Filter, we will likely have to do so at some point. Initially, the hypothesis was met with skepticism. The evolution of species on our planet has been going on rather smoothly, which means there may have been similar conditions elsewhere in the universe. In addition, the Drake equation shows that there should be at least several dozen advanced civilizations in the Milky Way alone. At least some of them are bound to have gotten the hang of radio astronomy or constructed spacecraft like our Voyagers. Consequently, interaction with an alien civilization is possible. However, ever since we set out in our search for other intelligent races out there, the universe hasn't dropped as much as a single hint of anybody else dwelling in its vast expanses. The hypothetical Great Filter may be the reason for this lack of clues. The hypothesis suggests that the role of the Great Filter may be played by one or several obstacles that advanced civilization has to power through in the course of its evolution. If a filter of this sort does exist, that should explain why we still need to receive signals from advanced civilizations elsewhere. Incidentally, the hypothesis admits that some creatures could survive the Great Filter. To do it successfully, they must complete several stages. First, their planet must be in its parent star's Goldilocks zone. Next, life has to originate and start evolving there, with organisms capable of multiplying using molecules like DNA and RNA. After that, single cells have to evolve into more complex ones, while the evolution of multicellular organisms will be vigorously stimulated. This, in turn, should stimulate the development of sexual propagation, which will benefit genetic diversity. Eventually, this will produce yet more elaborate organisms capable of using tools to develop to the level of advanced technologies necessary for space colonization. They will then colonize other worlds and stellar systems to ensure survival and obviate the eventuality of self-destruction. Robin Hanson argues that it is then, and only then, that the Great Filter will become a thing of the past within this concept. At the current stage of evolution, humanity should be bracing for the most challenging one coming next. Other celestial bodies must be colonized for the human race to survive. However, it is hardly necessary to point out that the plausibility of going through with this plan is rather small. Robin Hanson maintained that there is a fatal obstacle that an intelligent species encounters at some of the 9 steps of its evolution. This is supposed to be something definitive that causes the total elimination of the species. Humanity may have completed 8 steps of evolution. However, the chances of completing the 9th are slim, and that last step may be a fatal obstacle. Several other points are set out in the hypothesis. For example, it specifies measures that civilization must take to eliminate the risk of self-destruction due to internal wars, irreversibly detrimental impacts on ecology, and the depletion of natural resources. Apart from the exclusively theoretical benefits offered by this reasoning, it would be useful for working out our strategies for space exploration. From the perspective of the Great Filter theory proponents, the discovery of extinct multicellular lifeforms on Mars should be bad news. However, most of the steps we have completed have been easy, and so the greatest challenge will be posed by the steps still lying ahead of us. That is why the easier hypothetical evolution occurs on other planets, the higher the probability that humankind will never grow into a spacefaring civilization. But it isn't all doom and gloom. For all we know, we may have already negotiated our toughest obstacle at one of the completed steps. For this reason, some researchers believe that the fact that we appear alone in the universe is a good sign. This could indicate that we are the lucky few who have passed the Great Filter quite unscathed. Still, we can only admit that people use several forms of communication, whereas there may be considerably more of them. Either way, the universe is estimated to have existed for 13.8 billion years, and there may well be many organisms out there that would have overcome these obstacles, but only some of them will learn that there are others around. For this, they have to accomplish a major technological breakthrough, which in theory will be their undoing and lead to a global apocalypse. The situation on our planet demonstrates that we can eliminate the entire human race due to global thermonuclear war. The odds are rather high that our civilization will be wiped off the face of the earth before super-powerful engines or more effective forms of communication have been developed. It is also hard to identify the Great Filter, as other planets' environments may be completely different. For instance, abiogenesis, a process of inorganic nature transforming into organic, is bizarre and fascinating, and it may be a great filter for many intelligent races. Given all this, the Great Filter hypothesis prompts several important questions. Will humanity be able to adequately and successfully respond to an unexpected challenge, or is the worst already in the past? And the universe's silence is a sign that we are one of the few races to have completed all the stages devised by the Great Filter. Unfortunately, we cannot answer any of this today. However, it's hardly a secret. The distances in the universe are mind-boggling. Even with the best modern engines, a journey to the Moon will take several weeks and more than 6 months to reach Mars on the most optimal trajectory. If we think about the legendary voyages, after 45 years of traveling through space, they managed to leave only the inner part of the solar system. They're destined to spend several of the next millennia drifting through the scattered disk and the hypothetical Oort cloud. The fastest spacecraft is the Parker Solar Probe, whose speed in 2025 will be reaching a record-breaking 194 kilometers per second. However, this will happen only due to the Sun's gravity, which will never allow it to leave the environs of our star. And so the probe is doomed to soon burn up in its photosphere. Apparently, chemical jet engines, which are currently so widespread, have exhausted their development potential and are hardly suitable for interstellar travel. Of course, there are various alternative concepts, such as nuclear pulse propulsion or solar sails. But implementing either of these needs to be improved due to several serious issues. Most of these difficulties will likely be overcome sooner or later. Another important task for long-distance travel should be considered, namely creating a stable and powerful energy source. All modern spacecraft are relatively small in size and are equipped with reliable but low-power power sources. For example, independent research probes are usually powered by isotope batteries, which inevitably degrade over time. If we revisit the legendary voyages, almost all of their systems have long since been de-energized, and the spacecraft has been moving by inertia for many years. The ISS and other orbiting space stations use solar panels and radioisotope thermal generators, but their life support systems use the majority of their power, and the ion drives only serve to change their orbit. In the case of an extended crewed mission to a remote planet or star, however, a spacecraft would need much more power. Meanwhile, 99% of the way to another star inevitably passes through interstellar space, devoid of obvious energy sources. Even the radiation of the brightest stars is noticeably weaker here and dissipates in the vast expanses of space. Therefore, we need an independent, powerful, and preferably inexhaustible energy source to travel to other worlds. To figure out a possible way of solving this problem, we have to take a closer look at the universe's structure. Several amazing physical processes can be observed that contain a key to the star's secrets. To do this, we have to take a slight detour. In 2017, a collaborative effort of scientists from Princeton and Hong Kong yielded an incredible device that, at first glance, violates the fundamental laws of physics. A microscopic mechanism consisting of two-toothed silicon plates spaced 100 nanometers apart could generate a small amount of energy from nothing. Such a phenomenon should grossly violate the law of energy conservation, one of the fundamental principles of the universe's makeup. However, in fact, it is more complex than that. The amazing device is based on the Casimir-Polder effect, discovered in the middle of the last century. It boils down to this. If two thin plates are placed in a vacuum a very small distance apart, they will begin to be mutually attracted. The phenomenon is closely related to Heisenberg's uncertainty principle, which follows the existence of the so-called zero-point vacuum fluctuations. Pairs of virtual particles constantly appear at any point in the universe, by and large out of nowhere. However, their lifetime is only 10 to the power of 24 seconds, after which the particles disappear back into nothingness, and the global balance is restored. At the same time, virtual particles with any parameters are generated in open space. Only those that have strictly defined wavelengths can be generated between the plates. Consequently, numerous external particles press on the plates harder than internal ones. To illustrate, one can imagine that the space between the plates has a negative pressure. It's as if more substances were pumped out of the vacuum. The resulting mechanical tension can be transformed into an electric current, exactly what the Princeton and Hong Kong researchers did. And although the current was quite weak, it's the principle itself that matters, because this way our world receives energy virtually from nothing. Even a low-power source of inexhaustible energy is of enormous practical value. For example, as an autonomous power supply for microprocessors and other high-precision equipment. For example, the Voyagers, equipped with such a hypothetical battery, could transmit data from their instruments to Earth. This opens up promising vistas for exploring deep space. Many interesting physical phenomena follow from the Casimir effect, one of which is the so-called Scharnhorst effect. According to calculations, the speed of light in the space between the plates should exceed the standard value of 300,000 km per second, because there are no collisions of photons with virtual particles. Although modern technology still needs to allow this experiment to be carried out, its mathematical justification leads to far-reaching conclusions. For example, the widely known project of the hypothetical superluminal engine known as Alcubierre's bubble was proven to be feasible by scientists from Baylor University. Gerald Cleaver and Richard Odyssey combined the equations of quantum field theory and the general theory of relativity, producing a complex but clear rationale for a bold concept. It is worth mentioning that, according to quantum field theory, space has not 3 dimensions but many more. But this becomes noticeable only at the level of the microcosm. Applying the equations of this theory to calculate the Casimir effect, the researchers concluded that it is possible to control its properties with the help of a powerful energy impact. If we condense the space behind the hypothetical starship and make it more rarefied in front, an area appears similar to the Alcubierre bubble, capable of moving at superluminal speeds. The laws of relativity are not violated here because it is not the ship moving, but the space around it. On the other hand, the main problem with creating such a bubble from the beginning was the incredible amount of energy required. According to some calculations, an entire planet must be converted into radiation to form a sphere accommodating a starship. If researchers scale generators based on the Casimir effect to the required capacity, we can obtain energy anywhere in the universe, literally from nothing. Of course, there are still many problems to address for a starship to be fully operational because outer space is not the friendliest environment for humans. For example, it is permeated with deadly radiation, destroying living organisms' cells and causing negative mutations in their offspring. Thick metal shields or magnetic fields with certain parameters may be used as protection against it. Both approaches have their advantages and disadvantages. Another potential threat could be accidental collisions with micrometeorites and cosmic dust at high velocities. Even a tiny grain of sand has incredible kinetic energy and can pierce through a metal plate. Repair options are extremely limited on a long interstellar flight, and a hole in the hull may prove fatal. In addition, a long expedition without support from Earth requires creating a closed biosphere within the starship. Scientists from different countries are currently working on this. For example, various plants have been on the ISS for several years for scientific and consumption purposes. In addition, engineers are developing systems for recycling waste, including biological waste products. However, a fully fledged orbital ecosystem is still a long way off. The Solar System is just one of the countless planetary systems scattered across our galaxy. As we know, it consists of a single star in its main sequence stage and 8 planets with their satellites. In addition, our system contains over 1 million small celestial bodies like asteroids, comets, and meteoroids. Neptune is the planet in the system lying furthest, at least that we know of. Its orbit's radius measures around 30 astronomical units, equivalent to approximately 4 light-hours. Amazingly, only a tiny portion of the Solar System is encompassed by Neptune's orbit. The remotest object in the system discovered to date is the far out lying 132 astronomical units or 18 golden hours away from the Sun. Still, even this object, barely visible against a dark background of unfathomable space, is not close to the hypothetical Oort cloud, whose inner boundaries lie approximately 2,000 astronomical units away from the center of our system. According to some estimates, its outer boundaries stretch for up to 60,000 astronomical units, or at least around 1 light-year. These limits are predefined by the Sun's gravitational influence, and what lies beyond is interstellar space. Moving further away, we will notice over 50 of all kinds of stars within 20 light-years of the Sun. These stars are diverse, from dim and cold brown dwarfs to bright and widely known objects like Sirius, Procyon, and Altair. Some have planetary systems, with objects potentially capable of nursing and sustaining life. For example, the object known as Gliese 832c, 16.1 light-years away from the Sun, is more similar to our Earth than any other planet within the Solar System. The average temperature on the exoplanet's surface reaches 153 degrees Kelvin or 20 degrees C below zero, and it takes the astronomical body just 36 Earth days to complete a full orbit around its parent star. The distance between us and Gliese 832c is relatively small by astronomical standards. However, a space probe from our system, traveling roughly 17 kilometers per second, would take as much as 300,000 years to reach the exoplanet's environs. At our current level of technological advancement, it is impossible to design an interstellar spaceship capable of completing such a long journey. The Solar System and its neighboring stars are part of the Orion Arm. The latter, in turn, is part of the Milky Way. It contains around 400 billion stars, and potentially over 1 trillion exoplanets of all sorts can be discovered there, according to estimates today. The main diameter of the Milky Way measures around 100,000 light-years, and the stellar halo may be twice as large, even though the thickness of the main disk measures about 1,000 light-years. There is a clearly defined bulge in the galaxy's center. This bulge is roughly 3,000 light-years thick. The Milky Way is part of the so-called local group. This vast structure comprises over 50 galaxies concentrated within an area of space measuring around 10 million light-years in diameter. The Andromeda Galaxy, the Triangulum Galaxy, and the Milky Way are the largest of the lot. Some estimates show that the mass total of the cluster may reach as much as 3 trillion solar masses, with our galaxy and Andromeda accounting for the major part. With the distance from the Earth to Andromeda around 2.5 million light-years, It is considered our closest galaxy, not counting smaller or dwarf ones. Moving on to the next order, the local group forms part of the giant Virgo supercluster of over 30,000 galaxies. The supercluster is located within an area of space with a diameter of around 150 million light-years. Its mass total is as much as a quadrillion solar masses, or in other words, around 1,000 galaxies like the Milky Way. The supercluster is quite flattened, and around 60% of all the objects it comprises appear like a flat sheet around 10 million light-years thick. Staggering though it appears on the face of it, this value is small in terms of the universe's large-scale structure. As we zoom out, we can see a giant supercluster of galaxies approximately 520 million light-years in size. Called Laniakea, it includes several galaxy superclusters, including the Virgo supercluster and the Great Attractor. The overall mass of this formation measures approximately as much as 100 quadrillion solar masses. The Great Attractor lies roughly 250 million light-years away from our planet, and is the gravitational center for all objects lying close by astronomical standards. It cannot be observed directly from Earth, as the Milky Way's plane thwarts it. That is why the nature of the Great Attractor remains an unsolved mystery today. Laniakea is part of the large-scale structure of the universe, an elaborate system of galactic filaments, walls and voids, gargantuan areas of emptiness and space. Some of these objects are really enormous. For example, the Hercules Corona Borealis Great Wall stretches for around 10 billion light-years. Since his discovery in 2013, this superstructure has been considered the most gigantic component of the universe's large-scale structure. To all appearances, it must be home to millions of galaxies, and the number of stars it contains will likely defy calculation. The mere existence of a structure like that is a mystery to science, as according to today's accepted theory of the universe's evolution, gargantuan clusters like that are not supposed to form. But incidentally, this wall, so enormous that the human brain cannot fully appreciate its dimensions, is still just a tiny portion of the observable universe. According to today's cosmological notions, space in the universe continually expands, with the speed of expansion depending on the distance between objects. The further an observed object lies away from the observer, the faster the distance between the two increases. The rate at which the two objects mutually recede is not limited by the speed of light, because it's actually space matter that is expanding, which means that at a certain point, the two objects will be unobservable. Relic radiation observation shows that the area of the observable universe is a sphere with a diameter of roughly 93 billion light-years. According to the theory of relativity, we can see and interact with only those objects that are within this sphere. This conventional spherical area in space is called the metagalaxy, and it may be either all of the universe or, again, its tiny portion. For all we know, hypothetically, some unknown structures may lie beyond the visible boundaries of space. Such entities are referred to as different metagalactic objects, and unfortunately, it is impossible to study them today with scientific methods. Still, some astronomical bodies on the edge of the visible universe appear to be moving in ways different from what we would naturally expect, judging by the data we have. Instances of abnormal movements like those may be evidence of massive structures beyond the metagalaxy boundaries. Their attraction pervades the space around them and influences objects around them too. There are many hypotheses about the universe's structure beyond the metagalaxy, but most are rather metaphysical. For example, some people believe that time and space, as we know them, are non-existent beyond the universe's boundaries. This is because the physical laws there do not apply either, and notions of matter, materiality, or energy are virtually meaningless. This hypothesis is further elaborated on by the following idea. The meta-galaxy accounts for just a part of a more complex and larger-scale superstructure in space whose makeup and dimensions are too incredible for us to imagine. This structure could be in a multidimensional space or be based on physical principles we don't know. This makes the meta-galaxy an insignificant addition to, or partially reflects, this mind-boggling superstructure. According to some interpretations of the anthropic principle, there are other worlds beyond the boundaries of the observable universe. In those worlds, the values of fundamental constants like the speed of light or the electron charge are completely different. This hypothesis is in many ways supported by the idea of a multiverse, which schematically appears as foam with lots of bubbles separated from each other by thin walls. But these walls are impenetrable. This makes every universe a separate space with its own physical laws. And for all we know, these laws may be totally different from the ones we are used to. The most radical hypotheses go as far as to deny our world any objective reality whatsoever. According to these, the universe is just a simulation like virtual reality and computers, but on an incredibly advanced level. As a rule, ideas like that imply that some super beings or super civilizations are beyond the reality we are used to, whose level of advancement is infinitely higher than ours, and whose goals and capabilities are arcane and incomprehensible. However, it goes without saying that it is hardly possible to either confirm or repudiate these hypotheses. Of course, distances in space defy our imagination and are even frightening. They appear infinite from the point of view of any person today. Nevertheless, we know that the universe is expanding, and providing this process continues, there will come the point when space objects disappears one after another beyond the event horizon. First galaxies, then stars, and the world will immerse itself in eternal darkness. But by then, there will be no one around to witness that. In these lines, the famous American writer Ursula Le Guin expresses her thoughts through a character in her book. The word must be heard in silence. There must be darkness to see the stars. The phrase concerns the birth and death of all that exists. Every object in the universe has a beginning and an end. Some subatomic particles last as little as a tenth of a second. Some microorganisms live between 2 hours and several days. Man's life expectancy counts for several decades, but even stars eventually burn out after millions and billions of years of existence. And what about the universe itself? Is it also going to come to an end at some point? What will it be like, and what will happen after its death? The earliest theory of our world's genesis is known as the theory of the stationary or steady-state universe. Supporters of this theory claim that the universe has no beginning and no end. It has always been and always will be in a steady state of equilibrium. However, very soon, scientific estimations proved this theory likely wrong, as some irreversible processes are occurring in the universe. In the 1910s and 1920s, the Big Bang theory was formulated and widely popularized. Today, it is one of the most consistent scientific theories and can account for the universe's genesis and evolution. Dozens of scientists contributed to the development of the Big Bang theory, and Albert Einstein's works on the general theory of relativity laid the theory's foundation. The main conclusion this theory enabled scientists to arrive at is the supposition that the universe's fate depends on dark energy, a theoretical type of energy that causes space to expand. At this point, it is impossible to say anything definite about this physical phenomenon. There are a great number of theories about this, and each of them has its praiseworthy aspects and shortcomings. According to the data we possess today, the universe's age is calculated from the moment of the Big Bang and is estimated to be slightly less than 14 billion years. The universe is constantly expanding, and depending on the density of dark energy, it will either expand forever at a regularly increasing rate or slow down and reverse. In this case, the universe is bound to compress into an infinitely small singularity similar to what it originated from. Today, science is still determined to give a definite answer to the question, which of these two possibilities will prevail? However, it is ready to suggest at least two equally possible scenarios of what may happen next: the Big Rip and the Big Crunch. First, the universe's expansion rate is proportional to the distances between objects. The further some objects are located from each other, the higher the expansion rate. Imagine a balloon pumped with air. There are two dots on it. The dots will get further away if we pump more air into the balloon. That's the way the expansion of the universe works. It is space itself that expands. The further the dots are initially located, the faster they get further apart. At a certain point, this rate exceeds the speed of light. This point is known as the event horizon. All objects beyond it disappear from view and drift beyond the reach of the most advanced telescopes, never to be observed again. Imagine, first, the remotest galaxies and clusters will disappear from the sky. Then, one by one, the Milky Way stars will fade away. And to crown it all, it will be our turn for the sun to go dim. What a sad sight. If the Big Rip theory holds true, the universe's expansion rate will constantly increase. This will lead to expansion forces gradually overcoming gravity forces. After that, galaxy clusters, galaxies, and star clusters will be broken up. After that, it will be the turn of the stellar systems to disintegrate, as host stars will not have a good pull to keep their planets and satellites from floating away. At the next stage, matter will be reduced to atoms, and these will be reduced to subatomic particles. The matter will effectively cease to exist after this. Physical laws as we know them will cease, and any further developments are impossible to predict. Today's observations show that space expands, and the expansion rate is increasing. First, however, we need to familiarize ourselves with the nature of dark energy. It may have unknown properties which may reverse the expansion process. As a result, the universe will start contracting. This may happen if the general gravitation created by all matter in the universe exceeds its expansion force. This scenario is known as the Big Crunch. In this case, the processes in the universe will run similarly until their size decreases 5 times. Then, galaxy clusters will unite as one supercluster, filling the entire universe, considerably shrunk by this point. Meanwhile, events like the births and deaths of stars, planet formation, and so on will occur inside the galaxies. When the universe contracts 20 times more, its volume will account for just 1% of that of today's, and all galaxies will blend into one. The relic radiation temperature by that time will measure 274 degrees Kelvin, and it will continue to grow. This means that there won't be any liquid water left in the universe, and water is vital for biological life as we know it. Further contraction of space will cause the universe to heat up even more. Planets will first be burned and then melted. Finally, all matter will crumble into an enormous cloud of boiling plasma. After that, atoms and subatomic particles will disperse, and eventually the universe will collapse into a singularity similar to the one it used to be when it was born. There is a theory that is a spin-off of the Big Crunch theory. It is known as the Big Bounce theory. According to the Big Bounce theory, on reaching the state of singularity following the Big Crunch, the universe will be reborn due to yet another Big Bang, and the cycle will repeat itself again and again, supposedly forever. As far as it is possible to speak about eternity and conditions devoid of time and space, I will repeat myself by saying that our knowledge about dark energies is too meager to speak about the duration of any of these scenarios. For all we know, the next Big Rip, or Big Crunch for that matter, will take place during a period when there are still stars and planets around. But what if that isn't the case? What will happen to the universe if its ultimate fate remains extremely remote? Still, the laws of physics imply that the universe, as we more or less know it, cannot exist forever. There are 4 clearly defined epochs in cosmology, each associated with this or that particular phenomenon. First, we live in the so-called stellar era. There is a lot of interstellar gas in the parts of the universe around us. It is used as the raw material from which stars form. New stars are born from this gas, and the process will continue until all interstellar gas has been depleted. This epoch is expected to last from 1 to 100 trillion years. By then, the Sun and most other stars will have depleted their nuclear fuel, turning into white dwarfs, neutron stars, or black holes. I've spoken about it in an earlier video. The next era is known as the degenerate era. There will not be any main sequence stars around anymore. Most matter in the universe will remain in the form of white and brown dwarfs, and some matter will persist as neutron stars and black holes. It will take a great deal of time for all these objects to cool off, around a duodecillion or 10 to the power of 39 years. White dwarfs will gradually release their heat through radiation and become black dwarfs. As for brown dwarfs, they will cool off due to thermonuclear reactions taking place in their interior at a sluggish rate, and eventually stop completely. The most matter will be slurped up by black holes at this stage of the universe's evolution. Dark matter, annihilation, and protons. Disintegration will be the major process. The proton is a subatomic particle from which atoms known to science are built. It is considered one of the most durable subatomic particles. Its life expectancy, as it were, accounts for approximately 100 duodecillion or 10 to the power of 41 years. By the time this era ends, matter in the universe will look like a great ocean of freely floating elementary particles, with the occasional neutron star or black hole tucked away. The next era is the black hole era. According to some theories, black holes will form clusters and eventually blend together, thus forming one single gargantuan black hole. Alternative theories suggest that black holes slowly evaporate while emitting energy before vanishing completely. Black hole evaporation is a quantum effect produced by what is known as Hawking radiation. The smaller the hole, the more intensive its evaporation, eventually stripping the hole of all its matter and energy. This process is supposed to persist for 10 to the power of 100 years. This number is also referred to as a googol. As it may, eventually, only dead expanses of space will be left in the universe. This space will contain debris left over from processes in previous epochs. Photons, electrons, positrons, neutrinos, quarks, electrons, and positrons will collide, thus causing annihilation. The universe may exist in this state practically forever until the next big crunch or big rip. At the very least, either way, humanity will be long gone at that time. Its existence is likely to be terminated in the Stelliferous era. Our planet, meanwhile, will remain habitable for another billion years or so, and after that, it will be burned by the ever-intensifying glow of the Sun. About 5 or 6 billion years later, our Sun, by then a red giant, will shed its outer layers and become a white dwarf. But what will happen after the universe dies? As disappointing as it is, there is absolutely no way we can answer this question. The trouble is, whatever the scenario, there won't be either time or space as we know them. Even if the Big Bounce theory or the Big Crunch theory is right, a new Big Bang takes place, thus giving birth to a new universe, with a fresh set of galaxies and stars. We will never find out. We will never find out what it used to be like in the universe before ours, because the word must be heard in silence. There must be darkness to see the stars. The universe comprises countless objects bound together by the inexorable laws of physics. While in one part celestial bodies steadily orbit their stars for billions of years, violent outbursts in another part wipe out entire stellar systems in a matter of seconds. We only see a tiny part of the incredible diversity of the cosmos, and in its depths lurk many more great mysteries and riddles, and this means we'll enjoy many more fascinating journeys into the depths of the universe.